In this video we're going to look at curve sketching of a rational function. And my example is f of x is equal to x squared divided by x squared minus 4. So the first step is to get all the information we need from the function. And the first thing what we need is domain. So the domain of the function, and here in this function the denominator cannot equal 0. So what we need to do is set x squared minus 4 equal to 0 and solve for it, and we get x squared is equal to 4 and x is equal to plus and minus 2. So now we can see that this function does not exist at 2 and negative 2. So our domain is going to be negative infinity to negative 2 union negative 2 to 2 union 2 to infinity. And by setting the denominator equal to 0, we've also found where we have vertical asymptotes. Because we don't have an x plus 2 term in the numerator or an x minus 2 term in the numerator, both the places where the denominator is equal to 0 are vertical asymptotes. So we have vertical asymptotes, and I'm going to write it as VA at x is equal to negative 2 and x is equal to 2. Now for the horizontal asymptotes, remember we need to take the limit as the function goes to infinity. So we have the limit as x goes to infinity of x squared divided by x squared minus 4. And then we're going to divide everything by x squared to use the limit to infinity rule. So we have limit as x goes to infinity of x squared divided by x squared is equal to 1. And x squared divided by x squared is equal to 1 again, minus 4 over x squared. And that 4 over x squared term goes to 0. So we can go ahead and circle that to remind us that that's 0. And if that's 0, we're taking the limit as x goes to infinity of 1 over 1, which is equal to 1. So that means we have a horizontal asymptote at y is equal to 1. And the other thing we need is intercepts. I'm definitely going to try and get my y-intercept because we can just plug 0 in for all the x's. And when we do, f of 0 is equal to 0. We'd have 0 over negative 4, which is 0. So we have an intercept at 0, 0. And now we're going to do the first derivative test. So f prime of x is equal to, and remember this is the quotient rule, so we have x squared minus 4 times 2x minus x squared times 2x, all divided by x squared minus 4 squared. And now we need to simplify this. So the next step, I'm going to multiply everything together in the numerator. So I get 2x cubed minus 8x minus 2x cubed, all divided by x squared minus 4 squared. And I'm going to simplify it one more time. The 2x cubed and the negative 2x cubed cancel. So we have negative 8x divided by x squared minus 4 squared. And now we're going to set this equal to 0. So we have negative 8x is equal to 0 and x is equal to 0. And now we need to make a sign chart. So 0 is going to be our sign chart. That was our critical value. And then we can't forget our discontinuities. So at negative 2 and 2, we need to have spots on our sign chart. So now we need to check in each interval a number. So we're going to check f prime of -3, f prime of -1, f prime of 1, and f prime of 3. F prime of -3 is 0.96. F prime of -1 is 0.89. F prime of 1 is -0.89. And f prime of 3 is -0.96. So in our first interval, our number is positive, so we're increasing. In the second interval, we're also increasing. In the third interval, we're negative, so we're decreasing. And in the last interval, we're also negative and we're decreasing. So at 0, we're increasing and then we're decreasing. So here we have a max, a relative max. So we have a relative max at 0, and then we know what 0 is on our point. We found that there was an intercept at 0, 0. So this relative max is also at 0, 0. Alright. So now we need to do the second derivative test. So we're going to find f double prime of x. And remember, this is the first derivative that's in the simplest form. So now we're going to do the quotient rule again. So we have x squared minus 4 squared times -8 minus -8x times the derivative of the denominator, which is the chain rule. So 2 times x squared minus 4, subtract 1 from the exponent gives me 1, times the derivative of the inside, which is 2x, all divided by x squared minus 4 squared and squared. So if you notice, we have x squared minus 4 on both sides of our negative sign here, so it's in both terms and it's in the bottom, so we can simplify this. So we have one factor here that we can get rid of. We can change this into a 1 and get rid of one term, and then we have x squared minus 4 squared squared, which is x squared minus 4 to the 4th, and I'm going to change what it was as the 4th to the 3rd. And now I'm going to rewrite what I have remaining. It's going to make it a lot easier to simplify if you do that step first before you multiply everything together. So now we have -8 times x squared minus 4. So I have -8x squared. And then we have -8 times -4, so plus 32. And now we have minus, and we have a -8x, a 2, and a 2x. So we have -8x times 2 is -16x, and then times 2x is -32x squared. And since it's negative and we have a negative, it becomes positive. And then we have 32x squared, all divided by x squared minus 4 cubed. And now we can simplify that one more time as well. So now we're going to combine our x squared terms, and we have 24x squared plus 32 divided by x squared minus 4 to the 3rd. So now we can do the second derivative test. So the first thing we're going to do is set it equal to 0. So the numerator equal to 0. And when we look at this, we have an x squared term, so regardless whether we put a positive or a negative number in, it's going to become positive. and then we're going to add it to a positive number. So there's no way this can be 0. So we have no inflection point on this function. And now we're going to do a sign chart for the second derivative test. And remember, just because we don't have a critical value, we need to plot the discontinuities again. So we have -2 and 2. And now we need to test points in each interval. So this was our most recent f double prime of x. And we want to find f double prime of -3, f double prime of 0, and f double prime of 3. And f double prime of -3 is 1.984. F double prime of 0 is -0.5. And f double prime of 3 is 1.984. So in this first interval, we're positive, so we're concave up. In the second interval, we're negative, so we're concave down. And in the last interval, we're positive again, so we're back concave up. And now that we're done with the second derivative test, we need to tie everything together. So I've drawn a picture, and I've rewritten all the information so that we can see it all. And now we want to get it all down on the graph. So here, the first thing we want to look at, or the first thing that I like to look at, is the points that I know and the vertical asymptote and the horizontal asymptotes. So we know 0, 0 is a point on the graph. I'm going to put a dot there. I know I have a horizontal asymptote at 1. And I have a vertical asymptote at 2. And I also have one at -2. So now that I have my asymptotes drawn, I'm going to look at one quadrant at a time. So I'm going to look from -infinity to -2 first. And I can see that I need to be increasing and I need to be concave up. And whenever you have vertical and horizontal asymptotes like this, your function is generally going to go from asymptote to asymptote. So here, we're going to be increasing and concave up from asymptote to asymptote. And then in the middle, from -2 to 2, we're concave down, and we're increasing on the left of 0, and we're decreasing on the right. So from asymptote up, touch 0, 0, and now we're back decreasing, back down to the other asymptote. And in the last area of the graph, from 2 to infinity, we're decreasing and we're concave up. So we're going to go from asymptote to asymptote again. And that's how we curve sketch a rational function.